Howdy everybody, Steve here, KM9G. Today we're going to take a look at an oscilloscope. This is the GPIO 3-in-1 and it has an 80 megahertz range, which is really 40 up and 40 down, but we'll talk about that later. Let's get it opened up. In its natural environment, fairly easy to read screen. But indoors it is very easy to read. It's time to get dangerous. I'm what you would call a professional here. But what we're doing is 100% battery powered, so there's no chance of connecting mains to ground and killing myself. But we may destroy the meter. Let's go find out. I have an EBL battery here. This is 100% self-contained power, and it's actually a pretty nice little unit. I have a video on this on the channel. I will link at the top corner over there. And then we have the subject of today's video, the GPIO. I'm going to pull the bail out and set it over here like so we can see it. We'll turn it on. And then one of the things that this GPIO comes with is BNC on one end and alligator clips on the other. So we can do measurements of things with alligator clips. I'll plug that into channel 1. I'm going to hit the channel 1 button. We'll get you some better screenshots as time goes by. We're still doing dangerous setup stuff right now. And I have an AC plug. I'm going to plug this in enough so that it makes contact while also allowing me to plug in these alligator clips so they make contact as well. And we've got all these rubber booties and everything in place here. And the other end of this cord isn't going anywhere. It's right here. It's not important for the discussion we're doing right now. Yeah, that looks great, doesn't it? That looks nice and safe. And then, hi everybody, there's our screen. Luckily we can save these screen things. I'm going to turn the battery on now, and then I'm going to turn the AC on, and we should see some magic happen on the screen there. And the AC is on. There we go. It's trying to figure something out. I think our time reference is off. 500 millivolts, 50 millivolts, 20 millivolts, 10 millivolts. I'm going the wrong direction. Because this is going to be 120 volts. That's 10 volts. Per division. Oh, there we go. And then we'll save that by hitting the save button and save success. And then to recall it, we can go into waveform, and there she is on the bottom corner. Let's get into some better lighting and we'll take a look at it. And then here are the saved screenshots for you in an indoor setting. The screen looks really good. The camera's not doing it justice. You can totally see this thing outdoors and work with it, but the camera sees a different light reflection than your eye sees because of position of the camera and position of the sun and all kinds of stuff that doesn't really matter. It just works better with your eyes than it does with a camera. That's all that really matters. Another test for us all involves the battery. You'll see me do a lot of battery-based testing because I don't want to create ground loops between the power socket and the oscilloscope shorting back to ground through the oscilloscope. That would be bad for you, the human, and for the device that you just paid some good money for. So we're doing battery again, but this time we're doing a Raspberry Pi based test here. And this is a Raspberry Pi Zero, so, you know, it's probably less than $10 on the market now because this isn't the 02W, this is just the 0W. So single core processor, and it still has some good uses in the amateur radio world. Like this would be fantastic as an APRS server, receiver, transmitter, etc. But for right now, we're going to use it to test out some oscilloscope type stuff. So we're going to turn it all on, powering off of the battery, and I've got my ground connector hooked up to the shield on the USB port, and then I have the probe connected to pin 40, which is GPIO pin 21. Let's turn the scope on. Funny thing about GPIO pins on a Raspberry Pi is that the pin number, physical pin number on the board is not the same as the GPIO pin identifier. So pin 40 physical on the board is GPIO 21. So when you're doing your troubleshooting, make sure that you bring up that translation so that it's figure outable, because otherwise you're going to be on pin 21 wondering why you're not getting signals when they're all going out pin 40. So we're on pin 40 today. And what I'm going to do is I'm going to toggle it on and off and on and off, and we're going to see if the scope can pick that up. So in the background here, I have my laptop and I am SSH'd into the Raspberry Pi, and I have this little program called Blink. Let me see if I can bring it up in an editor for you. And that's all it does. Not really a whole heck of a lot going on there. It says that we're going to use red LED for pin 21, for GPIO pin 21. We're going to set it up as an output port with GPIO.out. And then we're going to tell the user to press Control-C to exit, because if they don't, it's just going to go through and toggle this over and over again. It's going to toggle it high, toggle it low, toggle it high, toggle it low. And this actually is a way to blink an LED if you were to build out a circuit. It's quite a simple project to do, but it gets the point across that the scope works, and that's really where we want to go. We want to start at the beginning and do some stuff. It's running. It says press Control-C to exit. Which light is that that's causing that reflection? That one. Awesome. That was easy. Okay, so we have our scope probe plugged into channel 1, so I'm going to hit the channel 1 button. I could just as easily hit channel 2, but I decided to hit channel 1. And we can already see that it is blinking and doing its thing here, and it looks very squarish. So what I want to do is change the volts per division. So now it's 1 volt per division. So each one of these little squares is 1 volt, 2 volt, 3 volt, and a little bit more. And we know that a lot of this stuff, let me see if I can get there we go. A lot of this stuff is 3.3 volts. And it looks like it's doing a 3.3 volt trigger. Let's bring that in, wrong direction, to 2 volts. So this is 2 volts and a little bit more, but not 4 volts. So still in the 3.3 volt range. But basically, you saw in the script that it was saying, go high, sleep for a second, go low, sleep for a second, go high. So that looks like it's doing the thing, right? Awesome. So the next thing I'm going to do, don't do this live while your device is on. I'm what you'd call a professional, and I get to do stupid stuff, so you don't have to. I've disconnected my probe from the Raspberry Pi, so you can see that the line isn't blinking anymore. It's not moving because I'm not telling it to. Up here, these top two pins, this first one over here, pin 1, is 3.3 volts, and this pin over here, pin 2, is 5 volts. So I put this on. We see it go almost to the 4 line. Remember, this is 2 volts per division, so the first division is 1 volt, the second division is 2 volts. Sorry, the first division is 2 volts, the second division is 4 volts, and we're almost at the 4 volt line. Let's switch that to 1 volt, and you can see that we're almost at the top. So 1, 2, 3, and change. Now if we switch this from the 3.3 volt pin to the 5 volt pin, it's off the charts because the scale only goes to 5. It goes slightly below 5. So there's 2, so we've got 2, 4, 6, and we're below the 6 line. So that's almost 5. Let's get a close-up on that. There you go. So 2, 4, almost 6 is 5 volts. And so if we change this again down to 5 volts, you can see that it's dead on the 5 volt line. It's producing a good 5 volts worth of electricity for us there. So pretty neat little test that you can do. And that, my friends, is basically what an oscilloscope is. It is a really glorified, impressive multimeter. And this thing also does multimeter stuff. The reason why it's a glorified, impressive multimeter is because it does multimeter stuff over time, not just period. So that's why you were able to tell it going up and going down. And if we had a better sample rate across the timeline, you could probably see when it switched from low to high, from 0 volts to 3.3 volts, you could probably see it ramp up just a little bit in that split second. And that would make that waveform that you're used to seeing over time. This scope can do 80 megahertz, and I believe it's 40 up and 40 down. So technically, you would think of it as a 40 megahertz range, but 40 plus 40 is 80. So there you go. This might just be your first oscilloscope, and as a result, I want to show you everything that it comes with it. So you get the oscilloscope that runs in regular scope mode, as well as running in multimeter mode for a variety of multimeter functions. So you can measure voltage in AC or DC, and it will show you the frequency. You can measure resistance, you can measure a diode, or you can do continuation, which we call continuity here. Or you can measure capacitance, and you can measure current in DC milliamp hours, AC milliamp hours, DC amps, or AC amps. And then it also has an arbitrary waveform generator, so you can pick the kind of waveform that you want, sine wave, square wave, ramp, and then you can use that as test input. It's going to output on the top pin, and then you can input it on channel 1 or channel 2. You could use that to compare different scope traces and kind of know what you're looking at. There are your channel ports, channel 1, channel 2, and the waveform generator out. And then down here at the bottom are your probe ports for the multimeter function. It comes with one regular oscilloscope probe with its ground lead, and then this has the yellow collars installed, but you get other colors of collars as well as a screwdriver to bring it into calibration, and some other tips to make your probe tip a little bit more precise and protected from touching other things you don't want it to touch. It is a USB-C device, so it comes with a USB-A to USB-C charging cable. I did try plugging this into the computer, and it does not have the ability to download images that I could find. You also have a BNC to alligator clip probe, so you'd have your positive and your ground, just like you have your positive tip and your ground. And then it has a set of multimeter probes. It comes with a simple operation instruction page as well as a larger user's manual. And then there's a handy-dandy carrying bag to put it all into. And then there I have everything shoved into the bag. I would not recommend putting all the probes and wires and stuff in there. First off, the probes are sharp and pointy and they'll poke through that bag. But second, it's kind of asking a lot of that bag. I would use the bag as a protection cover for the scope, and then I would put that other stuff inside of a box or something and carry that outside of the bag. That was the scope in a nutshell. There is lots of stuff that you can do with this, and we will be doing more stuff with scopes on this channel in the future. So if you like playing around with oscilloscopes and learning about different ways that different things work, this is the channel for you. Be sure you're subscribed. One of the things that I want to do is debug some output from some radios to make some future adapters so that I can do more amazing stuff, like push the tune button on the IC705 and have it make some changes so that I know that I pushed the tune button, and then I can feedback cat control and I can lower the power and all kinds of cool stuff. Also help with the memories because I'll know what frequency I'm on when I do hit the tune button. Or we've got that RT95 back from Retevis, and I want to debug the output port so I don't fry it again like I did the last time. Scope will come in big handy for that. There's a link for this scope in the description down below. And if you really want to get some pain and suffering under your belt, I've got a live stream linked for you as well, right over here, where we opened this up for the first time and went through it together on my Ham Nuggets Monday night show, where we do things that we don't know what we're doing, but we do them together. Thanks for being awesome. I'll see you over there.